In science, when we encounter a complex system that we want to understand, one technique we use is to create a simple model of the system. An example of this would be the ideal gas law. It's a simple model of how a gas behaves. And it turns out, in the case of the ideal gas law, that it does a great job of explaining helium gas. It does an excellent job of explaining that. And the great thing about these situations is, much like the ideal gas law, sometimes it does match reality, at least to some degree, but also because if it is successful, then we can build upon it, make it more complex. But the good news is we have a foothold, we have into understanding how it behaves, and that makes it easier to build these more complex models. So the situation we're talking about here, blackbody radiation, what physicists wanted to understand was the spectrum that an object will emit because of its temperature. And what they imagined is that they had some object that absorbed every bit of EM radiation that came upon it. And that's why it's called a blackbody, because it absorbs everything. And because it absorbs everything, it's going to get hot, and then it's going to emit some EM waves because it's going to have all these charged particles accelerating as they vibrate. And as I said, they'll emit EM waves, they'll emit some spectrum. And as a result, this was very successful. It turned out to be more successful than we really thought. It turns out that we can use this model here to really figure out the temperature of lots of different objects, not just stars, but really most anything. You can use it to get a decent approximation for the temperature of a panda bear. So this formula here is called Weans Law, and it says you take the peak wavelength times the temperature and you get this value. Now, what is the peak wavelength? Well, look at this graph here, which I got from Wikipedia. So this graph essentially is showing the intensity of the light, or I should say the intensity of a given wavelength, because over here on the x-axis we got the wavelength. And you can see that there's a peak. It goes up, and this is the peak. And then on this one, the 4,000K, there's a peak here, 3,000K, there's a peak here. But the point is there's some peak that corresponds to wavelength. And that's what this is. This lambda p is the peak wavelength. And it corresponds to the temperature. And we have this nice simple relationship that relates this peak wavelength to the temperature. And as I mentioned, you can use this to get an excellent approximation for the temperature of most anything. So certainly you can look at stars, you can determine what the peak wavelength is, plug it into this formula, and you'll get an excellent approximation for the temperature of that star, at least the surface temperature. You can also use this for people. So for example, let me do that right now. The average person's temperature, when they're healthy, is about 98.6 degrees Fahrenheit. That works out to be about 37 degrees Celsius. And we need it in Kelvin, of course. You can see that we have Kelvin temperature over here, but also just in general, if we're using temperature in a formula, then we need to use Kelvin. So in Kelvin, that's about 310. So we got 310 Kelvin. And if you solve for the wavelength, this works out to be about 9,355 nanometers. Now this graph over here is in micrometers, so if I convert that to micrometers, that's going to be about 9.355 micrometers. Okay, so if I'm looking at this graph, you can see here's 1.5, 2, 2.3. 9 is going to be somewhere way over here. And it turns out infrared goes out quite a ways. This is infrared. We do not emit much visible light, but we do emit infrared. And so, in fact, not only do we emit infrared, but most every living animal on this planet, at least that's of a suitable size, is going to emit primarily in infrared. And so if you're using infrared goggles, you can look out and you can easily identify the animals because they emit heavily in infrared.